Johan, thanks a lot for a kind introduction. So today I would like to tell about small game theory for stability analysis of infinite networks with nonlinear components. We would like to analyze this problem using the synergy of Lyapunov methods and theory of nonlinear monotone systems. Before I start, I would like to say thanks to my cooperation partners who come from various fields of our science, from nonlinear control, dynamical systems, functional analysis, and electrical engineering. So thanks you guys for great cooperation within the last 2 years. Many of the results which I would like to present are a part of this cooperation. We live in the world of networks. We are surrounded by social networks, manufacturing networks, electrical grids, transportation networks, and due to the emerging technologies like cloud computing, Internet of Things, 5G, these networks grow in size and in the number of connections to other subsystems. The safety and reliability of such networks need to be analytically verified. And existing tools do not always scale to this kind of complex systems. It is known that in many cases, the infinite networks capture the essence of large but finite networks with possibly unknown number of components. Today in this talk, I would like to present the tools which will help us to analyze infinite networks with nonlinear components for stability and robustness. So assume that we have a network which is an interconnection of some systems sigma I. Each subsystem sigma I we will assume to be a finite dimensional system which has the external input ui, and it obtains also the inputs from other subsystems. And these inputs are just the states of the neighboring subsystems. We will assume also that each of these subsystems is individually stable. And the main question will be for us, under which conditions an infinite interconnection of nonlinear stable systems will be again stable. So we consider an interconnection of countably many systems, sigma I. The state of sigma I we denote by xi, and this is a vector in Euclidean space. We assume that all, well, okay, you may think that all these spaces have Euclidean norm, but in fact, our results allow to any choice of the norm for each subsystem sigma I. So basically, some of them may have the Euclidean norm, another infinity norm, etc. So, okay, the state of sigma I is xi. Xi bar is consisting of the states of the neighboring subsystems which influence sigma I. For the sake of the presentation, we always assume that we have only finitely many neighbors which can influence the systems. Although in some results, we allow also for infinite number of neighbors. Ui is an external input to the system sigma I, and we also assume that it is finite dimensional. So fi is some nonlinear function which we assume to be continuous function in all components. So now we have fully described the subsystems of our network, and now we would like to describe the whole interconnection. To this end, we combine all the individual states of subsystems into the vector x, all external inputs into the vector u, and all right-hand sides into the vector f. So now we can formally write the equation of motion for the whole network in this way. X dot equals f of xu. So this looks like an ODE, but in fact, this is an infinite dimensional system because x is infinite dimensional. So now in order to fully describe this system, we need to introduce the state space for it. For this talk, we will choose that X is L infinity. So this is the space of all infinite sequences such that the supremum norm is finite. As I have told, the individual norms for each xi may be of different type, but they should be fixed in advance. So this space is also called L infinity sum of the spaces R and I, and it is well known that it is a Banach space. Analogously, the space of input values will be also L infinity space, and the space of input functions we assume to be the space of piecewise right continuous functions from L infinity space. We equip this space of input functions with a natural, essentially supremum norm, and in fact, since our functions are piecewise right continuous, this boils down to supremum norm. Okay, so we have this system and we assume that we have also initial conditions. So then we obtain this initial value problem and we need the concept of solution for it. So we call a continuous function lambda a solution for this system if this map is locally Bochner integrable and lambda satisfies such an integral equation. So this is precisely the mild solution in sense of Kara-Teodori, so as we know from the ODE study. So here we use precisely the same solution concept. We will always assume for this talk that the solutions exist and are unique for all initial states and external inputs. So, and one can naturally, using Lipschitz continuity of F, derive this property. So we have fully described our system. Now we would like to introduce the stability properties. To this end, we will need the following classes of comparison functions. So k-infinity functions are functions which are 0 at 0, continuous and increasing to infinity. KL functions are functions which are 0 at 0, increasing, also continuous in the first argument, and they decrease to 0 monotonically in the second argument. Now we can define one of the key concepts for this talk. We say that a system is input to state stable if the trajectory of the system can be upper bounded by a sum of two functions. Beta function of class KL, so it's increasing in the first argument, which is the norm of the state, and it decreases with the time to 0. And another sum element of this sum is the gamma function, which is of class K, and it describes the influence of the input. So basically, the asymptotic behavior of the system, the maximal deviation, asymptotic deviation from the origin. If U is identically 0, so the system is undisturbed or has no input, then this guy vanishes and our trajectory converges to 0 uniformly on bounded balls, because this function beta decays to 0 when time goes to infinity. If the U is non-zero, then there is no guarantee that we will converge to 0, but we will converge to the ball around the origin with the radius gamma of norm of U, which depends only on the norm of U. So then in some sense, we have a kind of, if we start here, if X is identically 0, then we have automatically a bound for X in terms of the input. So therefore, ISS unifies the stability in the sense of Lyapunov together with input stability, input-output stability, let's say. So why is one interested in ISS? Well, because it provides a unified theory of internal and external stability, as I have told on previous slide, which is very appealing from the mathematical point of view. But that's only a beginning of the story. So in fact, ISS is very important for nonlinear robust control and observation of nonlinear systems. So various techniques for control of nonlinear systems have been developed based on this concept. And also it is crucially important for analysis of control of networks. And this will be the main aspect for us for today. There is a number of surveys on ISS theory. So this classical survey by Eduardo Zonta on finite dimensional theory, the recent book by Karafilis and Kristich on ISS of PDEs, and a recent survey by Christophe Prieur and myself on ISS of infinite dimensional systems. So now, before I will present the main problem in the precise terms, I would like to describe general idea on a simple example of interconnection of two systems. So we have here an interconnection of two systems, sigma 1, which has state x1, and sigma 2, which has the state x2. So they are coupled to each other. So x1 goes as an input to sigma 2, and the state of the sigma 2, which is x2, comes as an input to sigma 1. So in this way, they interconnected, and we call the coupled system sigma. And we would like to study the stability of both systems. We assume that both of them are ISS. And, well, we can write down what does this mean. This means that the norm of x1, so of the state of the first subsystem, is up bounded as this sum of this KL transient term and this another term, which describes the influence of the system sigma 2 on the system sigma 1. And since sigma 2 is also ISS, we have the similar estimate here with some functions gamma 2, 1, which describes the influence of the system sigma 1 to the system sigma 2. So you see, yeah, so here we already plug, instead of the input here x2 and here x1 as an input to the second system. And now it turns out that if the composition of these two gains, which describe the influence of systems on each other, if the composition is less than identity, then also the whole system is input to state stable. Well, sometimes we need to scale them a bit, just very slightly, but since I'm just describing in general ideas, so this is a nice condition to describe. So if this composition is less than identity, then the whole network will be input to state stable. Moreover, if the Lyapunov functions for these subsystems are known, then Lyapunov functions for sigma can be constructed. So for ODE systems, these fundamental results have appeared in the middle of the 90s by Zhang Tilprali and Zhang Mariels Wang. And I'm really happy that Yuan Wang is also here with us on this talk. So I'm really happy to see her here. And afterwards, it was extended to the couplings of N systems by Dashkovsky, Karafilis, Zhang, Grufa, Wirth, Ito, and many others. Since the small gain methodology was extremely successful for ODE systems, afterwards the main results have been extended to time delay systems, hybrid systems, general infinite dimensional systems like PDEs, etc. And it was always leading to great success. However, all this was for finite networks. And interestingly, in parallel with this development, another research direction was thriving. This is the development of spatially invariant networks theory. The idea of spatially invariant network is that we have an infinite network of subsystems which are coupled to each other. But what is the meaning of spatial invariance? This means if we look locally at the system, so we take some node of the system, then, and look also at the neighbors, then this type of interconnection of each node to the neighbors is the same. So locally, the system looks the same. It doesn't matter at which node we just scale and look closer to this system. Using this rich structure, and also using, as a rule, the linearity of subsystems, a very powerful theory has been developed for this kind of infinite networks. Finally, very recently, the research in ISS theory for infinite dimensional systems has been started. And I have thought, together with cooperation partners, that actually it would be great, based on the recent advances in ISS of infinite dimensional systems, to develop the small gain theory for infinite nonlinear networks without probably any assumptions of spatial invariance, and which will be working also for systems whose subsystems are nonlinear. And today I would like to present the result in this direction. The basic concept which helps us to analyze the stability are Lyapunov functions. So as a rule, if we have a nonlinear system and we would like to prove its stability, then we construct a Lyapunov function for it. The same story is also with input of state stability. And we have a suitable concept of ISS Lyapunov function, which is a continuance function mapping the state space to the positive numbers or non-negative numbers. So we must satisfy this sandwich estimates. So here psi1 and psi2 are k-infinity functions. So in particular, they're 0 and 0 and increasing. So hence also v is 0 at 0. And also the other property must hold. So if x is large enough with respect to u, then the derivative of a Lyapunov function with respect to trajectory, so in this case we use the upper right Dini derivative, so this derivative must be negative, and actually it should be upper bounded by this term, minus alpha of v of x. Okay? So if u is identically 0, we plug it in here. So if the system is undisturbed, then this guy vanishes. So this is 0 then. And then this implication tells us if x is non-zero, then the derivative of a Lyapunov function must decay in this way. And then we obtain precisely the usual definition of a Lyapunov function for global asymptotic stability property, which we know from the undisturbed systems. And in fact, one can show that if there is an ISS Lyapunov function, then the system is ISS. If so-called big property holds, so boundedness implies continuation property. And conversely, if the system is ISS and in addition we have sufficiently regular right-hand side, then input of state stability implies existence of an ISS Lyapunov function. For ODEs, this result was proved by Eduardo Zontag and Yuan Wang in middle 90s, and recently it was extended to infinite dimensional systems by Fabian Wirth and myself. So basically, we have a nice concept of a Lyapunov function which helps us to analyze the stability. Now I would like to use it for infinite networks. Another concept, however, which I would like also to introduce is a so-called monotone homogeneous aggregation function. So here by L infinity, we understand the space of all bounded sequences, as you remember, so uniformly bounded sequences. And L infinity plus is a positive cone in this set. So these are all infinite sequences which are uniformly bounded and whose entries are non-negative in each coordinate. So a function mu defined on this positive cone and mapping its elements to the non-negative numbers together with infinity is called a monotone homogeneous aggregation function if it is homogeneous, monotone, and subadditive. And now we can make the main assumption for this talk and for the results which I'm going to present. We assume now that we have an infinite network. And each subsystem in this infinite network is input to state stable. And even more, we assume that we have an ISS Lyapunov function Vi for this system. Furthermore, we assume that there are functions psi1 and psi2 which do not depend on I, so which are uniform for all subsystems, such that Vi satisfies this sandwich inequality with this psi1 and psi2. So in general, clearly we can construct Lyapunov functions which do not have such uniform psi1 and psi2. So in general, we just have Lyapunov function. For each function, we have its own bounds from below and above. But if they cannot be lower bounded and upper bounded respectively in a uniform way, then basically we will not be able to study stability of the network using small gain methods. We are completely out of business then. So we really need to assume this uniformity in the sandwich bounds. So this is one assumption for Vi, and the second one is again this implication, which tells that if the state is large enough with respect to the input, then the solution decays. And again, you see, we assume that each Lyapunov function decays along the trajectories with some uniform decay rate alpha. So what is the difference to the previous definition? The difference is here, so in this input. Earlier, we had only this term. So if Vi is large enough with respect to some input external, then we had this property. But now the input, we have not only external input, we have also internal inputs from other subsystems, and they are described in this way. So this guy describes the input from other subsystem, from subsystem with a number j, right? So one could write down instead of the Lyapunov function here the norm, right? Because we have here this sandwich bound, so we could write down here the norm of xj, but it is much better to write here vj, then the formulation of results is much better. So we take this here. And here these gamma ij are some coefficients, so these are just numbers, which we understand as the Lyapunov gains. So okay, this guy describes the influence of the subsystem J on the system I. But now I would like to combine all these inputs from all subsystems together. So in order to understand what is the total input of all subsystems onto this subsystem I. And to this end, we have here also this aggregation function mu I, which is assumed as homogeneous, subadditive, and monotone. Okay, so what does this function do? It takes the inputs from all subsystems and combines them into one big input. How does it do it? Well, for example, this mu I can be just a sum. Then we say, okay, the total input is the sum of the inputs of subsystems. But for some application, it is better to have here supremum. So then we say that the total influence of the system on other subsystems is the supremum of the individual influences of subsystems. Okay, so we are really flexible here. Also, mu I can be a combination of both. So some inputs are added to another, and then some other inputs, we take maximum of them, etc. So we allow here for a great deal of flexibility. So these mu I are nonlinear, but subadditive and homogeneous, and these gamma ij are linear, right? Then we will have also nonlinear result, but for a while, let us assume these guys are linear. So now we have these nice Lyapunov functions, which characterize the stability of individual subsystems and the influence of subsystems at each other. Now I would like to aggregate this information into one gain operator, which we define in this way. So this operator gamma mu, so it depends on this mu and on all the gains gamma ij, and it's defined in this way, right? So we just basically take what we see here and plug and define this as our gamma. And now instead of Vj of xj, we write just as j. Okay. So this gamma mu maps then positive cone in L infinity to positive cone. Okay, so, and it describes, let's say, the interconnection structure and the influence of subsystems at each other. And now it turns out that in order to study the stability of the infinite network, what we have to do is to analyze the properties of this gain operator. So if it is, let's say, small enough, then we can conclude the stability of the network. But now we have to understand what does it mean small enough. So we have to know more about the properties of such operators. And this is what we're going to do next. Well, first of all, we need to assume that this operator is well defined, because clearly in general it does not have to be. So, but this is quite easy, so we can just assume this bound. So if this property is satisfied, then the operator is well defined. So then, since we know that these aggregation functions are monotone, subadditive, and homogeneous of degree 1, then it is easy to verify that also our gain operator is monotone, homogeneous, and subadditive, where these properties are formalized as usual. Okay, so this operator is actually quite nice, has many nice properties. Even better, these three properties taken together already imply continuity and even Lipschitz continuity of this gain operator. So the operator is really good. And now we have to study its properties, further stability properties now. To this end, it makes sense also to introduce the discrete time systems. Now take just an arbitrary operator gamma. So maybe it is one of this gain operator which was previously, but in fact it does not have to be. So we just consider general discrete time systems of this form. But we assume that gamma is homogeneous, and for homogeneous operators gamma, we can define the concept of spectral radius using this formula. So in fact, I mean, this is the reminiscent of the formula for spectral radius of linear operators, Gelfand's formula. So if gamma is linear, then what we have here is just the Gelfand's formula for positive operators, positive linear operators. And now we can characterize the exponential stability of this system governed by the operator gamma, which is monotone, subadditive, and homogeneous of degree 1. And now we know that the following conditions are equivalent. The fact that the spectral radius is less than 1 is equivalent to uniform global exponential stability of this system. And this, in turn, is equivalent to existence of a point of strict decay, which is a point which lies in the interior of the positive cone. So what is this interior? Interior of this L infinity plus, this is the set of points which are uniformly bounded away from 0. So they cannot, let's say, converge to 0 in their coordinates. So they must, each component must be uniformly stay away from 0. So, and I mean, it's not enough. So we need that this point is this interior of the cone, and also that our operator at this point is less or equal than some lambda times this point where lambda is less than 1. So basically gamma uniformly decays in each component of this vector. So therefore this result provides a criterion for uniform exponential stability of such systems. So I would like to prove one of these implications, which will be of prime importance for the next developments. So I would like to show that 2 implies 3. So this means that exponential stability, so A here, the decay rate, it is less than 1. So we assume that the system is uniformly globally exponentially stable with the decay rate less than 1. We take any point lambda, which is between A and 1, so it is also then less than 1, any vector y from the interior of L infinity plus. So for example, we can take just vector of all i's, all ones, and we consider the following vector Zn, which is this sum, if n is finite, but we can allow also for n be plus infinity. Then we have a series here. Okay, so if n is plus infinity and gamma is a linear operator, then you immediately see that this is a series expansion of the resolvent of gamma. Okay, well, just note, I mean, clearly if n is finite, then this is some vector in L infinity plus, which is easy to see. If n is equal to plus infinity, then it is again well defined because this series will be absolutely convergent, right? So this we can obtain just using the exponential stability. So gamma k of y is upper bounded by m times a power k norm of y, and now we can use that a is smaller than lambda, and this series converges, so this is less than infinity. So this series is then absolutely convergent, and since our state space X, L infinity, is a Banach space, then it is also convergent. So this vector is well defined for all such n. Okay. Now, since gamma is monotone, this vector is also upper bounds this vector y scaled by 1 over lambda. And since y is in the interior of our positive cone, then also this vector is in the interior of the positive cone. Well, it's already good, so now decompose gamma applied to this vector in the following way. So we just subtract lambda times identity, add lambda plus identity, substitute this expression for Zn, and now we use the properties of our operator gamma. Since gamma is subadditive, I can put it here, right? So here n is finite. I mean, if n is infinite, we can still work with that. But if n is finite, I can directly apply the subadditivity and basically put gamma here inside of the sum, which I am doing also here. So now we can apply homogeneity of degree 1 and take this coefficient out, which I do here. And now the life is good. Why? Because now we can subtract from this sum this guy. So from this sum, what remains is just one term. And what remains from this sum is just the term for k equals 0. And we have this guy. But now this term in fact converges to 0 when n goes to infinity. And so because y is in the interior, then at some point, so at some n, this old term will be non-positive. And so we will have here, we can upper bound it by just lambda times Zn, if n is chosen large enough. Okay, so then what we obtain? We obtain that this vector is well defined, lies in the interior of the positive cone, and our operator gamma uniformly decays at each component of this vector. So this means that this vector is the point of strict decay of our operator gamma. So which is nice. I mean, we have not only shown the existence of such point, we have also shown how we can explicitly construct it. Well, okay, you may say, good, we say that this holds for large enough n. But in fact, if we know the coefficients m and a in the definition of uniform global exponential stability, then we can even estimate how large should this n be. So we really have an explicit construction then. Well, good. I mean, in fact, we are interested primarily in the stability of infinite networks. But what we have proved right now is the criterion of for stability of discrete time systems. And I mean, this is an interesting problem on itself. So there are many people who work with that without any kind connections to small gain theory. So if we think about this problem from this point of view, then it makes sense also to pose it in a bit more general way. So then we are not interested only in x equal to L infinity. So then we just take x an arbitrary ordered Banach space with some closed cone and some subadditive monotone operator, which governs the dynamics of the system. We again consider the same system we had before, right? But now it is not on L infinity plus, it's on the positive cone x plus of the Banach space x. And what we would like to do is to characterize now uniform global exponential stability of this system using small gain properties of gamma. So, well, we do not have such results. So it's an open problem right now. So what we believe is true is that our criteria for uniform global exponential stability, which we have proved for x L infinity, should be extendable to the case when x is an ordered Banach space and its positive cone is normal and with a non-empty interior. So we think this should work. It is harder and more challenging how to characterize this property if gamma is normal and is just generating cone. So we do not have a solution to this problem, but this will be really interesting what one can say in this direction. So we have some results also in this respect, but it is not fully solved. But if gamma is a linear operator, then we have such results, and they are currently here in this paper by Jochen Gluck and myself. So which, well, it's written submitted, but in fact, it's already provisionally accepted to Positivity Journal. So, okay, we have obtained this characterization of exponential stability for discrete time systems in infinite dimensions. But in fact, it seems to be new also in the case of finite dimensional, in the finite dimensional case. Well, if gamma is not, at least if gamma is not linear and not max linear. So in these two cases, there is quite a lot of theory clearly. So actually, in the finite dimensional case, we can prove one more equivalence, which is also of interest. So if gamma is again monotone, subadditive, and homogeneous operator, then this condition, so let's say exponential stability of the induced discrete time system, is equivalent also to existence of a path of strict decay with respect to gamma. So recall we have had a point of strict decay, which is a point such that gamma decays at this point with some linear decay rate. So here we assume that the decay rate is nonlinear, right? So, and it is given by some function rho. But we do not only decay at some point, we decay at some path, which is described by this sigma. So, well, in one direction, the proof is very easy. So if we have a point of strict decay, then it's easy to see that we can construct a path of strict decay. The converse is actually not that easy, but it can be shown using the properties of the decay sets, which are developed in these papers by Deshkovsky, Rufa, Wirth, and here Rufa and Zyla. Okay, so actually we will see also this concept later in this talk. Now we go back to the analysis of stability. And now we can show our first main result for today. Assume that we have an infinite network, which is well posed, satisfies the so-called big property. So boundedness implies continuation. Well, it basically means if our solution is uniformly bounded, it can be prolonged to a larger interval. So we cannot really develop, it cannot be that the solution evolves and then just stops while being bounded. So if it stops in finite time, it must go to infinity. So this is basically the property which is almost always satisfied for that class of systems which we have here. So it's a very mild restriction. So we assume well-posedness and we assume this property. We also assume that we have ISS Lyapunov functions for each subsystem as we have defined previously. So we have here uniform bounds, uniform sandwich bounds for all vi. And we have also that if xi is large enough with respect to input, then the Lyapunov function decays with respect to trajectory with some decay rate which is uniform with respect to I. And the influence of subsystems at each other is described by these gamma ij functions, which are gains, and these aggregation functions mu i's. We again define the gain operator as previously using these functions, and we assume that the spectral radius is less than 1. So we assume that the discrete time system, which is induced by the gain operator, is uniformly globally exponentially stable. So also we assume that our functions vi are Lipschitz continuants on bounded balls and with constants which are uniform in I. Under these conditions, we can show that there is a point of strict decay of the operator gamma such that v of x, which is the ISS Lyapunov function for the interconnection, can be constructed in this way, just as a scaled supreme of vi with the scaling coefficients given by the inverses of these coordinates of this vector. Okay. And now what is important? So this is a point of strict decay of the operator gamma, right? And we have shown that we can explicitly construct this point of strict decay. So this means that we have an explicit construction of a Lyapunov function for the whole network with known these coefficients, which is quite nice. So now, one more time, some highlights of this result. We have some infinite network. If we can find Lyapunov functions such that the gains are linear, Lyapunov gains, and some possibly there are aggregation functions which are subadditive and homogeneous, then we have a natural small gain condition which is in fact tight, so it cannot be relaxed in general. We have also numerous equivalent restatements for this condition. I have presented just some of them, but there are in fact further restatements. One can have Lyapunov conditions ensuring this property, etc. So there is a very rich theory for that. Furthermore, we have a simple formula for ISS Lyapunov function of the interconnection, and even these coefficients can be computed in this way. For large enough n, and this n can be again estimated. So we have very rich information about this Lyapunov function. And if we have that gamma is linear operator or max linear operator, then we have even more information, which I, however, don't want to present today. Okay, so in this case, we have a really also quite strong result in terms of the computation. So it can be really it is easy to apply. However, clearly in this case, the gains should be linear. And these aggregation functions, which extend our result to the slightly nonlinear case of homogeneous and subadditive systems, also have to satisfy some properties like this subadditivity. Now let us turn our attention to general nonlinear case. So what we can do in this direction. And in fact, we can. So now we assume that all subsystems again have Lyapunov functions. So we again have the same sandwich estimates, and we have similar implication here. But now we assume that our gamma ij are no more linear functions, but they are general nonlinear k functions. And also, we do not have a general aggregation functions. We assume now that we have them always in the supremum. So we assume that the total influence of all subsystems over the system sigma I is given by the supremum of individual inputs of the neighbors. So this is clearly more restrictive than we had in the previous case, but on the other hand, we have here really general nonlinear functions. So now our gain operator takes this form. This is clearly now a nonlinear operator, and we don't know whether in general, so it may be not even well defined or be not continuous, but we will always assume that this family of the gains is pointwise equicontinuous. And this will ensure that our operator is well defined and continuous. Okay. Now, to require existence of points of strict decay is too restrictive for this generic nonlinear case. So instead, we introduce another notion. We call a map from R plus to our positive cone a path of strict decay for the operator gamma if each component is k-infinity function. All the components are uniformly bounded from below and above by some k-infinity functions. We have some regularity here for the inverses, so like Lipschitz continuity of the inverse. And also we have this important property, that there is a k-infinity function such that gamma decays on the image of this. Well, it decays along the path of strict decays. And our decay rate is, however, nonlinear function. Okay. So previously we have been working with the points of strict decay. So it was just one point, and at this point we have some linear decay rate. So here since we are in the nonlinear world, we need to assume the existence of nonlinear decay rates in general. And now we have the following result, which is the second main result for this talk. So we assume the existence of Lyapunov functions in this way. We construct the gain operator from these gamma ij's. We assume that there is a path of strict decay for the gain operator. And we assume again that all Lyapunov functions Vi are Lipschitz continuums on bounded balls, and these Lipschitz constants are uniform in I. Then the following function is an ISS Lyapunov function for the whole network. So again, we take our Lyapunov function for the network as a supremum over Vixi, but now our scaling coefficients are nonlinear and are given by the inverse of the components of this path of strict decay. One can also show that this function V is in fact locally Lipschitz continuance outside of 0 and continuance at 0. In particular, sigma is ISS. Okay. So what we have here, what is the main difference? Well, the main difference in assumptions clearly that we are here in a more general situation. We have general nonlinear gamma ij. So this is like a positive side of this theorem. We're in a generic nonlinear case, but here we have this assumption. So we assume that there is a path of strict decay for gamma. And in fact, it is not easy how to check this. In the previous homogeneous subadditive case, we needed just to compute the spectral radius of gamma, or to check the stability of the corresponding uniformly, the stability of the corresponding discrete-time system induced by the gain operator. It was like an easier problem than checking whether there is a path of strict decay for the gain operator. However, something we can do also here. And therefore, for the next part of the talk, we would like to analyze under which conditions we can ensure this existence. Before doing that, I would like to relate this small gain theorem to other results. The first small gain theorem for infinite networks with nonlinear gains was this paper by Dashkovsky-Pavlichkov in Automatica in the previous year. So there they have developed the small gain result for infinite networks under assumption that all gains are nonlinear but are equal and less than identity. So basically, it is not possible that some gains are larger than identity, as it was the case in finite dimensional, as in the small gain results for finite networks. But all gains must be uniformly less than identity, which is quite a strong restriction. So what we can show that if gamma satisfies even stronger condition, like a bit stronger, it's not only less than identity, but we can find also k-infinity function so that gamma is less than identity minus this k-infinity function. Well, it can be arbitrarily small, but still in k-infinity. So if this condition holds, then we construct a path of strict decay, which is extremely simple. And then we can apply the results in our paper to recover the main results in this paper. However, if we do not have such eta, so if we have really this condition, then we cannot recover the results from here. However, as I have told, in our theorem, we can allow for nonlinear gamma ij, which are distinct and larger than identity. So we are significantly more general in most situations. In this result, the small gain theorem was developed for nonlinear gains, provided the linear path of strict decay exists. So in our case, we can recover this result. So if we assume that our path of strict decay is linear, then we fully recover this result. But in the theorem which I have presented, we do not need the linearity of the path of strict decay. However, we base on a number of results from this paper. In particular, in our analysis, when do the path of strict decays exist, we rely on many developments which we initiated here in this paper. So good. Our next, in the final slides of this talk, I would like to discuss when do the path of strict decay exists. Before thinking about case of infinite networks, let us think about finite dimensional situation, because here we have a nice and strong result. Consider our gain operator. Then the following statements are equivalent. So existence of a path of strict decay is in fact equivalent to the condition that the system generated by the operator gamma, but a bit larger than that, is uniformly globally asymptotically stable. So basically what we do, we take our gain operator, we choose any row, consider identity plus row combined with gamma, and consider this discrete time system induced by this enlarged gain operator. And your guess of such systems is equivalent to existence of a path of strict decay with respect to gain operator. But also this is equivalent to this condition, that our gain operator slightly increased never increases outside of zero. So we have no point where this operator increases. So this is called strong small gain condition. And in fact, this is equivalent to this condition, which is what we call uniform small gain condition, which is always stronger than this one. Well, good. Okay, in the finite dimensional situation, it is equivalent, but in infinite dimensions, for in L infinity plus, this will be always stronger than that. So this result is probably never stated in precisely this form, but it can be derived from the main results in this paper by Dashkovsky, Rufa-Wirth, this paper by Bjorn, and this paper by Kavan, Gluck, and myself. Okay. So we have had a very nice result in finite dimensions, and unfortunately in the infinite dimensions, the situation is much more complicated. Well, maybe not unfortunate, so that's life, hard life in infinite dimensions, but it's also very interesting life. So currently the relationship between the following three conditions is unclear. So between this uniform small gain condition, between existence of a path of strict decay, and between the stability of this induced system. But what we were able to show that a certain combination of uniform small gain condition together with the U-guess property of this system implies existence of a path of strict decay for gamma. I will not present the full development of that result. It's really interesting. I mean, there are many important questions in that way. I would like just to present this lemma, which was shown by Dashkovsky, Schmid, and Wirth, and myself, which is about the properties of so-called strong transitive closure. So we assume that gamma is our gain operator, and then if we assume this kind of small gain condition, well, I will not explain this meaning, just think about some kind of small gain condition here. Then the strong transitive closure of the operator, which is defined in this way, well, Q is precisely this, what is called strong transitive closure or Kleene star of the operator gamma, then it is well defined and satisfies such nice conditions. So let us think about what does this operator mean. So what we have here, so gamma k of S, when k goes along all non-negative numbers, this is basically the trajectory then. And we take the supremum of all states along which the trajectory goes, right? So basically what is this vector? This is the vector which majorates all the trajectory which the system starting in S comes, right? So, I mean, it's unclear whether this operator is continuous in general, which properties does it have, whether it is well defined, but we were able to show here in this lemma that if a kind of small gain condition holds, it is well defined. And it has some nice sandwich bounds from below and above. And furthermore, each point in the image of this operator is actually a point of non-strict decay. Okay, so it's actually a nice point, right? Because what we need is a strict decay, but well, at least having a sufficient number of points of non-strict decay is already a good idea, already a good start. So how we proceed next with this lemma? Well, then one has to analyze the properties of this Kleene star operator. Well, continuity, properties of its image, topological some properties. One has to obtain information about the sets of decay of the gain operator, and then using some more regularity of gamma ij, one can construct the path of strict decay. Still, although we have positive results, so we can really show that under some kind of small gain conditions, we have the existence of the path of strict decay, but still it's not a result which is sufficiently final. So it is not as nice as what we have in finite dimensional systems, and much more investigations are needed here. Furthermore, this analysis basically works only for this type of gain operator. If we change here this aggregation function and take something different, like summation or some mixing of supremum and sum, or maybe something else, then our analysis will not work. So one has really to invent something completely different. And for that case, the problem is fully open. Now we come to the conclusions. So what we have discussed. One of my main messages was that the synergy of Lyapunov methods and methods of nonlinear monotone systems theory is a powerful tool to analyze the stability of finite and infinite networks. We have discussed the nonlinear small gain theorem for infinite networks. If there is a path of strict decay, then the network is input to state stable, and we can construct a Lyapunov function in this way. We have also sufficient conditions for existence of a path of strict decay based on the so-called Kleene star operator, or strong transitive closure of gamma. If gamma is homogeneous and subadditive, then in fact we have a very nice small gain condition. We need just to check the spectral radius of the gain operator, and if it is less than 1, then the network is input to state stable, and we can construct the Lyapunov function in a very easy way, and even these scaling coefficients can be found using an explicit formula, which gives us very nice conditions, computationally quite good for linear or max linear systems or combinations of them. We have also a number of open problems. So the relationships between small gain conditions for nonlinear discrete-time systems are not really clear. So we have to understand these nonlinear discrete-time systems governed by gain operators much better. If we have the understanding of them, then we will be able to have much better tools also for stability analysis of infinite networks. Also, nonlinear small gain theorems are shown only in max formulations. So it would be nice to have more general formulations of the Lyapunov small gain theorems. Also, better understanding of the stability of monotone discrete-time systems is needed. And finally, I would like to present here these references. So these are papers on which this talk was based. So the first one is a paper which is about the nonlinear small gain theorem for infinite networks, where we also present our sufficient conditions for existence of paths of strict decay. In this paper, we analyze the properties of infinite networks governed by homogeneous and subadditive gain operator. In this paper, the small gain theorem for nonlinear infinite networks with linear paths of strict decay was proved, and here the notion of strong transitive closure was analyzed for the gain operator. Well, finally, in this paper, which is not directly related to what I have told, but here we have a small gain theorem, nonlinear small gain theorem for ISS of infinite interconnections without using Lyapunov functions. So here it is so-called trajectory-based smogging theorem. Well, if we do not, let's say if we cannot construct Lyapunov functions, but we can verify ISS using different types of estimates, then this is the paper which will then give strong tools for analysis of interconnections. Also, what is interesting here in this paper, we have analyzed not only networks of ODE systems, we could work here also with the networks whose components are of different types. So then we may have ODE components, time delay components, PDE components, combinations of them. So it's like a much more general framework. And I assume that the results which I have presented today can be also formulated using in this more general framework, using the machinery which is developed in this paper. Well, finally, in this paper with Jochen Gluck, we have the stability criteria for positive linear discrete time systems. So again, as I have told, if we would like to understand the property of infinite interconnections, we need to know the properties of the corresponding discrete time systems generated by gain operators. And here we have solved fully the problem for the case of linear operators. So therefore, this can be understood like a guideline for what one could try to achieve in the nonlinear case. So at this point, I finish my presentation. Thank you a lot for your attention, and I hope you have enjoyed this, and I would be happy to hear your questions. Thanks.